We go.
Okay, hello everyone. Today we're going to talk about our term project, which was based off of the paper Time Series Anomaly Detection using diffusion-based models by these three authors. I'm Spencer.
Jonathan.
And I'm Jeremy.
Okay, so the introduction to the problem is straightforward. Anomaly detection in multivariate time series is a really important field and a really important problem to study. This has a lot of applications such as uses in industry for predictive maintenance. And there are a bunch of methods to do so. There are classical methods such as these, and there are also deep learning methods, and these usually use transformers, scans, or RNNs. And so these deep learning approaches can be broadly sorted into two categories, forecasting based and reconstruction based. Essentially, it tries to learn the data set. Anomalies by their nature do not follow the general trends or patterns of an of the input time series. So when the model tries to predict or reconstruct these, it will be way off and it's anomaly. So yes, the objective of the original paper was to show how diffusion-based models, which are widely used in image synthesis, can be used in this sort of reconstruction-based anomaly detection. And in fact, these sort of models have already seen some use in detection of image anomalies. So basically, can be applied to temporal data as well?
And the original paper proposes three new models, which are composed from two base architectures, transformer-based autoencoders and diffusion model-based on unit architectures. Um, there's one on just using autoencoders, one using just using diffusion-based models, and then the best performing model would be diffusion AE, which is a combination of diffusion and autoencoder.
And as you can see here, the results of the three models that they developed outperformed previous models in other papers.
All right. And so for my changes, my first idea was to apply PCA for dimensionality reduction and to reduce noise by projecting input data onto principal components to simplify learning for the model. I did this by applying PCA while retaining 95% of variance to the raw time series data before converting it into windows for model input. However, I noticed that PCA actually degraded performance due to loss of crucial nonlinear and temporal information, indicating that it's not really beneficial for this context. So then I scrapped that idea and decided to do the opposite and try to add more noise to improve. And the motivation behind that was to improve robustness by forcing the network to reconstruct clean signals from noisy inputs, thereby making it easier to highlight anomalies. I did this by injecting Gaussian noise with a noise factor of 0.1 into training inputs and use mean squared error loss between the denoised output and the original clean signal. After that, I tried a separate, different approach and worked with the unit architecture, transforming the linear attention and making it into full attention. I did the motivation behind this was to enhance the model's capacity to capture global long-range dependencies and time series data. I did this by replacing the linear attention blocks in the unit's down and up blocks with full self-attention modules. Although by doing this, it required more memory usage, so I had to reduce the number of heads and the dimensions. And here are the results for my denoising autoencoder and full attention implementations. As you can see, the denoising autoencoder performed just as well on F1 scores compared to the baseline models of diffusion AE, and then actually performed even better with ROC and AUC scores. But the full attention scores were just slightly under the baseline model, but I attribute that to a lower number of heads and dimensionality.
All right, so the changes I made were mainly to the diffusion model. The rationale was that the autoencoder outperformed both diffusion-based models on the real-world data. And the main difference between the real-world data and the synthetic data that we use was that the real-world data had no anomalies in its training data, while the synthetic data did. So the idea is that the diffusion-based models were not reconstructing the original data series accurately enough. So, especially if there are no anomalies. So if you improve the performance of the diffusion model, then you improve the reconstruction, you improve its ability to reconstruct the input data series, and it's easier to detect anomalies. So to do this, I made changes to the base unit architecture. I noticed that unlike other implementations of the unit architecture, the ResNet blocks used did not have a convolutional layer after the CLU activation. So I tried adding that. As well as that, I also tried to use residual blocks for upsampling and downsampling between resolutions in the unit architecture. So you can see my results here. The baseline is the baseline as presented by the original authors. Diffie4 is simply was adding the convolutional layer in the ResNet blocks. You can see it actually degraded performance. Diffie5 includes both the convolutional layers and the residual blocks for upsampling and downsampling. You can see the performance is actually better, slightly better than the baseline with regards to ROC AUC. And finally, Diffie6 only has the residual upsampling and downsampling blocks, and you can see that it performs the best.
So these are my changes. So first was adding a cosine scheduler and replacing it with the from the linear one. So the scheduler controls how noise is added to the diffusion training. By using the cosine scheduler, we introduce noise in a way that prioritizes low frequency patterns in the data. And because low frequency signals are preserved, the model creates smoother reconstructions. And therefore, anomalies become harder to reconstruct, leading to larger reconstruction errors. And by amplifying that error or the difference between the normal and abnormal signals, that improves anomaly detection abilities. The second change was a temporal transformer block. And so it captures relationships across extended periods in the time series data. And the existing spatial attention, which was in their implementation, is used to target local relationships between different channels. And to implement this, we converted from a spatial grid into a time sequence. And after temporal processing, the data is returned to its original spatial format for further processing. And by having both, the model gains a more comprehensive really view of the data and understands what an anomaly would look like. And the third change was implementing a variational autoencoder. So it predicts basically the mean and variance of the signal, and the loss function we used for that was combining the reconstruction error and with KL divergence, like how closely the learned distribution aligns with predefined Gaussian prior, and the variational autoencoder can represent multiple valid variations of normal data. And this approach helps distinguish genuinely anomalous inputs from typical variations, and integrating the VAE with diffusion methods further clarifies anomalies as anomalous data stands out more. And as you can see by this table, the three different approaches which were tested individually showed a general improvement over the original diffusion autoencoder model, which was their best model.
And here are some challenges and some future work that we've reflected on. Our biggest challenge was a time constraint. Like everyone else, we shared the Wave HPC, and our group specifically struggled because we had 7 data sets that we needed to train on, and that's primarily why we decided to focus on the real world data sets instead of the synthetic ones. Also specifically for my implementations for the full attention, with more GPU resources and not having to lower the amount of heads and the dimensions, full attention might have performed even better. We also see that changes did not improve F1 score or RC values across all data sets. And some future work would be just more hyperparameter fine-tuning, like noise factor, or to combine all of our most successful changes together to see what improves more.
And in conclusion, the original paper shows strong performance for anomaly detection with their methods, and our results show that there are many potential improvements that could be made, as was discussed prior, that could improve on top of what the original paper had proposed. Thank you for listening to our presentation.
You didn't show the thank you slide, bro. I was trying to show you.
Okay.
Oh,
Oh,
I don't think
We do not have really much time
Okay.
left to do anything.
yeah. Just clip that shit and
Honestly, not bad.